Okay, this is the Unit 2, Lesson 11 video, and we are in Chapter 8, Section 4 of the textbook, and this lesson is about graphing rational functions. So we have two content standards again, and I'm pretty sure they're the same as the last lesson, which are creating equations in two or more variables to represent relationships between quantities, and graph equations on coordinate axes with labels and scales. I just want to emphasize it's really important that when you graph your equations on coordinate axes that you do label your axes, you label your scales, that you don't just assume the person looking at your work is going to understand what your scale in your mind was that you used when you made the graph. And the second content standard says compare properties of two functions, each represented in a different way, algebraically or graphically or numerically through a table or by a verbal description. And our mathematical practice that we're going to focus on is looking for and making use of structure within the problem. So we've already graphed reciprocal functions, which we did in lesson 10. And in this lesson, we're going to graph rational functions that have vertical and horizontal asymptotes. And we're also going to graph rational functions with oblique asymptotes and points of discontinuity. So rational function is a new term for you probably, but you know rational just means ratios, which means fractions. We talked about vertical and horizontal asymptotes already. Oblique asymptote is probably something that's new, and a point of discontinuity might also be new to you, but we'll explain this when we get there. So here's our table for vertical and horizontal asymptotes. I'm going to try to blow this up a little bit. So it says you have a function that's a of x over b of x, and a of x and b of x are polynomial functions. There is a vertical asymptote when b of x equals 0. So if the denominator is 0, whatever x value makes the denominator equal 0, there's a vertical asymptote. It also says f of x has at most one horizontal asymptote. So it either has no horizontal asymptotes or one horizontal asymptote. And the way you can check for the horizontal asymptote would be if the degree of a is greater than the degree of b, there is no horizontal asymptote. So if the top function has a higher power than the bottom function, there's no asymptote. If the top function a is less than the bottom function b, the asymptote is 0. And if the degree of the top function a and the bottom function b, if they're the same, then the horizontal asymptote is the leading coefficient of a divided by the leading coefficient of b. So for example, if we had, let me write this up on the screen. If you had a function that was, say, like 3x squared, and then a whole bunch of other stuff after it, over 4x squared with a whole bunch of stuff after it, because these are both second degree powers, because they match, your horizontal asymptote would just be 3/4, 3 over 4, which is say y equals 3 over 4. So here you can see pictures of each of these three scenarios. The first scenario is where there is no horizontal asymptote, and you can see that on this piece of the function, there's no value that the graph approaches horizontally. And over on this piece, there's no value it approaches because it keeps going up to infinity and up to infinity, down to negative infinity, down to negative infinity. There's no actual numerical value that it approaches. And you can see that from the function here, the top power is x squared, the bottom power is just x to the first, so the top power is bigger. Whenever the top power is bigger, there's no asymptote. And then if you look at these other ones here, the bottom power is bigger, so the asymptote is 0. You can see on this piece it goes out to 0, and this piece approaches 0. And on this last function, we have 2x plus 1 over x minus 3, so they're both x to the first power, so the horizontal asymptote would be just 2 over 1, and you can see from the left side it approaches 2 from the bottom. From the bottom it's coming up to approach positive 2, and on the right side it's coming down from the top to approach positive 2 as you go out to infinity. So our first example, we're going to do a function that where there's no horizontal asymptote. We have to graph x cubed over x plus 1. So the first thing that you want to do when you're graphing one of these rational functions is to find the zeros. And you find zeros by finding whenever the numerator equals 0, which is the a of x function. So on the top we have x cubed equals 0. And because that's just a single term, it's a monomial, we can just take the cube root of each side, and we're just going to get the number 0. So there is a 0 at x equals 0, which means the function crosses the graph at x equals 0. Step 2, you're going to look for asymptotes. So we're going to look for a vertical asymptote, and we know the vertical asymptote is when the denominator equals 0. Our denominator was x plus 1. So we're going to solve that equation for x, and we get x equals -1. So there's a vertical asymptote at x equals -1. And we need to remember that the degree of the numerator, which was x cubed, is greater than the degree of the denominator, which is x to the first power. So that means there's not going to be a horizontal asymptote because the top power was bigger than the bottom power on this equation. So now we're going to draw the graph. In order to draw the graph, you want to use some different table values. So you're going to pick some x values, plug those x values into the equation, and see what values you get out. Your output values are your y values. So all of these things in the table are just coordinate points. So they've come up with these values. And then the next screen, I'm sure they're just going to show you a graph, but I want to show you on a grapher how that stuff actually comes out to play. So this is one of my favorite websites. It's called desmos.com, desmos.com. I really like this for graphing. Obviously, you can also use your graphing calculator, but I'm going to recreate the table of values that they used. So we had -3 and 13.5. And -2, 8. Let's see, it's easier if I just hit tab to just do all the x values. So -1.5. I don't know why they did a half. I'm just gonna, oh, well, whatever. -1.5, -0.5, 0, 1, 2, 3. I think that's what they had. Oh, +0.5. Okay, fix that. Okay, my y values, 675, -0.25, 0, 0.5, 2.667, and the last one, 6.75. Okay, I'm going to zoom out a little bit so we can see those points. Okay, so if you just look at these points, this is kind of confusing probably. You're not really sure what this all means. So I'm going to throw in the function that we had, x cubed over x plus 1. Did I graph this point wrong? 0.5, -0.25. 0.5, -0.25. Let's make sure I put all these other numbers down correctly. -2, 8, -1.5, 6.75, 0.5, -0.25, 0, 0, 1, and 0.5. Maybe I typed the function wrong. Let me go to the next screen over here. X cubed over x plus 1. X cubed over x plus 1. Huh. This is probably, oh, this is supposed to be -0.5. Did I mess that up? Let me go back to the previous screen. Okay, this is supposed to be -0.5 here. Obviously, because it's to the left of the 0 on the table, this should have been negative, and they messed up and they didn't put the negative sign in there. So when I add that negative sign in over here, you can see that the graph does touch that point now. So this is what your graph looks like. This one I think is probably hard for you to figure out. If I take off the graph itself, come on, I don't want the point there. Okay, if this is all you see when you're plotting your points, it's going to be hard for you to figure out where on earth you put the line to connect it. So you might want to come up with some more points closer into 0 because we have a you need to well, basically you need to find when the vertical asymptote is, and remember that was when the denominator equals 0, so around -1. So they jumped to the -1.5 and -0.5 because those were the closest values they wanted to get to -1. They were half a unit away on either side of it. But let me put this graph back in. You can see how this is -1.5, and as we go close to -1, there's a vertical asymptote. Maybe a good thing to do would be to put in that vertical asymptote, x equals -1. And you see if we throw in that vertical asymptote, you can get a better idea. As these points come down, if I take the graph off, as these points come down, they have to go back up here so that they are along that vertical asymptote. And over here, as these points go up, but to the left of it, they need to come down and approach this vertical asymptote. So that'll give you a better idea as to how to line up your graph with the points once you put the vertical asymptote on your graph. So if we move back forward again, and we can see that their picture, it looks pretty much the same, but they obviously have a slightly different graph. They didn't use the graphing program that we used. So that was a long explanation for one example. Here's one for you to check your progress on. We've got x cubed over 2x minus 1. Go ahead and pause the video and work out the horizontal asymptotes and the vertical asymptotes, and then pick some points and sketch a graph for yourself. And when you have your answer, go on to the next screen. All right, so our answer for this one is choice A. Pretty crazy looking graph in here. It would be better if we could zoom in and see that picture a little bit better. But you can do that on your Desmos app or your graphing calculator if you want to look at that. We're going to end the video here and pick up with example 2 in the next video.